what relates vapor pressure to temperature? Clausius flat line. So the natural log of pressure 2 over pressure 1 equals delta H of vaporization divided by R times 1 over temperature 1 minus 1 over temperature 2, right? And in this case, I've given you 2 temperatures and 2 pressures. What can you solve for? Heat of vaporization. Make sense?
God damn it, I knew that.
So heat of vaporization would equal R times the natural log of P2 over P1 divided by 1 over T1 minus 1 over T2. You could clean that fraction out without super reason too. That'll give you heat of vaporization. I'll do it in a second. Then once you have that, how do you go back in the normal boiling point? I go back to this equation, and now I'm going to find the temperature that goes with 760, right? Make sense? And then we just solve for that temperature. So here, 8.314 joules per mole Kelvin times the natural log. Doesn't matter which one you call which, I'll just call them 1 and 2 for simplicity. 231 over 46.1 divided by 1 divided by temperature 1. So you added the 273 to 299.15 minus 1 over 324.25 Kelvin. You okay with that? And I have on my paper that kicked out 51,780. What would the units on that be? What's the confidence? Just look at the algebra. Logarithms are unitless, right? What are the units on bottom? Bottom is big fraction. 1 over Kelvin. So you get joules per mole. And I'm not going to round that yet because I'm going to use it, right? Then I'm going to plug in natural log of, I'll call 760 over, you could use either point you want. I'll use the first one. Equals 51,780 joules per mole divided by 8.314 joules per mole Kelvin times 1 over T1. So in this case, I use the 299 again. You could use either temperature minus 1 over T2. Let you solve the algebra. T2 turned out to be 345.68 Kelvin. And if you want to subtract 273 from it, you can. Does that make sense? One person got that right that I glanced at. What gave us trouble? Again, that's an identical problem. The only difference was on the homework, it gave you ammonia. This is chapter 11, almost everybody's done this. It gave you ammonia, and it gave you 5 data points because technically what you do is a graph. Most of us would do that. But, thoughts?
I didn't know what I was doing, but I got confident.
Okay, you got the delta H?
Yeah.
And then you just didn't know what to do the other part?
Yeah.
Because the problem I gave you on the last quiz, I think, was like delta H vaporization. So you formed the sheet and I asked you for the boiling point, right? So what's the second half of this one? Just the data given. Here's a potential test type question. Graphically, how could I go about finding heat of vaporization? If I wanted to do this graphically, which is what the homework intended for you to do, of course, how could you do it graphically? How you'll do it in the lab? What would you plot to find heat of vaporization? Good.
Regulate your pressure by temperature.
So which one on X, which one on Y?
Pressure on X and temperature on
So plot pressure here, temperature there. Thoughts? How would we know? What's the logic? I wouldn't care about the answer, I care about the why. This was the 2-point version of Clausius Clapeyron, right? The 1-point version, which is where it came from, was the natural log of pressure equal, if I remember correctly, you have it in a formula, negative delta H of vaporization over R times 1 over T plus natural log of some constant that we've talked about yet. Remember that? Y equals mx plus b. What would I plot on the x-axis?
What do I bring?
1 over the temperature.
1 over the temperature. Make sure you have temperature in Kelvin. And what would I plot on y?
1 over heat.
Natural log of the pressure. And I'm going to get a line from something like that. And what could I do? The slope of that line is negative delta H over R. So delta H is equal to negative R times M. You multiply the slope of the line with negative R. And that gives you heat of vaporization. Make sense? So, things like that, A, could be good multiple choice questions, and B, the next chapter does dozens of those with different forms, so we have to be good at graphical analysis. All of kinetics in chapter 13 will use graphical analysis. Damn algebra. All right, question 2, which is also an 11. Temperature of solution form 25 grams of ice. I'm gonna go a little faster on this one. Energy is conserved, right? So the heat changes the ice and the heat of the water. Which one of these is gonna be positive, left or right? Which one's gonna be a positive heat? I'm just waiting to get a consensus. The ice will melt, therefore the ice to the left side is positive. It's taking energy in, right? The water side is losing energy, right? So it's negative. And these have to be equal and opposite. I'll put the negative sign where it's convenient. The ice is going to melt, so the mass of the ice divided by the molar mass of water times the heat of fusion plus the mass of the ice times the specific heat of water times temperature final minus temperature 0, because that's where it started. That's the energy gained by the ice. It melts and then it heats up, and it heated up from 0 where it started after it melted. The water just has a change in temperature, so it's the mass of the water, specific heat of the water, temperature final minus temperature initial of the water, and easier to put the negative sign there. And what variable are we solving for? TF. In this case, it's rather nice because this is 0, right? So I can take mass of the ice divided by molar mass times heat of fusion plus the mass of the ice, specific heat of water, let me add it over there, equals negative mass of the water, specific heat of water, temperature final minus temperature initial of the water, minus mass of the ice, specific heat of water, temperature final, and we distribute and divide. What gave us all the trouble in this problem? That's my question. Because that's really your question. We've done 3 versions of that now. Good. But it's not always the same. It's whatever the energy term was. This idea is going to show up in every chapter. Conservation of energy. Energy left somewhere, energy went somewhere. Whatever energy left had to be equal to went somewhere, just opposite signs. It won't always be heat. Equations will change. It's just the idea is the same. Mass of the ice divided by molar mass times diffusion. Let me not write. So I'm going to take negative mass of the water, specific heat of water, temperature final, plus mass of the water, specific heat of water, temperature initial of the water, minus mass of the ice, specific heat of water, temperature final. I'm going to subtract that from that side, factor T sub F out of this. Mass of the ice divided by molar mass times heat of fusion equals negative T sub F, no, let's do this. minus mass of the water, specific heat of water, temperature initial of water, equals negative T sub F times mass of the water, specific heat of water, plus mass of the ice, specific heat of water, which means I could have factored that out also. So temperature final equals mass of the ice, molar mass, heat of fusion, minus mass of the water, specific heat of water, temperature initial of water, divided by negative specific heat of water times mass of the water plus mass of the ice. At that point, we have all the numbers. If the ice started out at 0 degrees Celsius and the water started at 32, what do we know the answer has to be? Between 0 and 32, right? I saw multiple answers that went either side of the other way. That tells you the logic. Check it. Does that make sense? Just to see the numbers here. So mass of the ice was 25.0 grams. Molar mass of water is 18.01528 grams per mole. Periodic table. Heat of fusion was 6,020 joules. Mass of the water was 120 grams. Specific heat of water is 4.184 joules per gram degree C. Times temperature initial of the water, which was 32 degrees Celsius. And I'm going to divide that by negative 4.184 joules per gram degree C. 120 grams plus 25 grams. Real quick, look at our units. What would the units for our answer be? Just from the math, not from the logic. What will the units for that term be? Now what will it be? Joules. What will the units for this term be? They have to be, right? Their energy. Top is joules. What are the units for the bottom? Joules per degree Celsius. So joules divided by joules per degree Celsius is degree Celsius. And the answer was 12.1. I think I've lost my page. Any thoughts on that one? Because we've done several versions of that one now, and I thought that one's going to be better. 12.7 degrees Celsius. Thoughts? And I'm worried you're just used to give me a formula, I'll plug numbers into it. We build systems. We take fundamental ideas and we put them together to build systems so we can do stuff later. I'm here with this here, so take a break. How many grams of magnesium? What's the formula for magnesium chlorate? Again, if we can't write the formula, there's not a whole lot we can do. Although if you write the wrong formula and do the rest of the work right, that's 1 point. Wrong. If you do it symbolic, that's even better. What's the chlorate ion? ClO3, -1 charge. We have to know nomenclature. Can't do anything without it. That's magnesium chlorate. So how many grams of magnesium chlorate must be added to that many grams of water to raise the boiling point, normal boiling point, to that? So delta T equals I times K sub B times molality, right?
Yes.
And what's our definition of molality? So this is I times K sub B times mass of solid divided by molar mass of solid divided by the mass of solvent, and that's in kilograms, right? And what am I trying to find here? Mass of solid. So M sub A equals delta T times the mass of B, we'll have to follow our units, times molar mass of A, divided by I times KB. Delta T here, what's the normal boiling point of water? 100. So we have a 3.2 degree C difference. We have 1.1 kilograms of the water. The molar mass of potassium chlorate is 191.2074 grams per mole. What is I for magnesium chlorate dissolving in water? 3. It'll break into 1 magnesium ion and 2 chloride ions, right? In case of B for water, 0.512 degrees Celsius per molal, and that will produce grams when you're done, 438 grams. Again, identical to a homework problem, except they did freezing point. Other than that, they use the same number of grams. And instead of using magnesium chloride, they use potassium chloride. Other than that, it's the same. 18 people got that one right. Thoughts on that one? What got us? So if this doesn't help it get better, we don't need to spend the time on it, but this is the kind of part where you're looking to see what will fix it for us. And lastly, what volume of 0.758 molar ammonium carbonate is required to produce that many grams? What's the formula for ammonium carbonate? Well, ammonium ion, which we have to know is NH4 plus 1, carbonate CO3 minus 2. So ammonium carbonate is NH4 2CO3. Let me ask you this. Why do we think we're so bad at nomenclature? Because that was an early Chem 1 and intro/high school requirement. So why is it we're doing so bad at nomenclature?
Not enough practice.
So molarity, what's our definition of molarity? Moles of solute over liters of solution, right? So this would be mass of solute divided by molar mass of solute, same thing, moles, divided by the volume of the solution. And here I'm solving for volume of solution, right? So volume of solution equals the mass of the salt divided by the molarity times the molar mass. So you would have had 29.6 grams divided by 0.758 molar times ammonium carbonate's molar mass is 96.08612 grams per mole. And what will they give you for units? Liters. So you can report the answer in liters or milliliters. It was 0.406 liters or 406 milliliters. Again, I changed the salt. I didn't change the two numbers in the homework. All right, we're going to take a break in a second and come back, and then we'll start working the review. However, when you do the review, the goal is not to go to my notes, go to the book, and look up how to do it, which is what we've been doing in the homework, I'm guessing. The purpose of the review is, I don't know how to do this problem. What is it I don't know so that I can make myself a note to go fix that? The review is not the exam. They're not the same questions. They're not the same. I'm not one of those people I give you the same questions and change the numbers.